Hey there, in this video we are going to learn about mixture problems. In particular, we're looking at some kind of container that has a mixture in it and it has more solution coming into it. So there's an input rate involved and then there might be substances coming out of it as well, so an output rate. So the differential equation that can describe a situation like this is dx dt equals the rate in minus the rate out, okay, where x of t is the amount of substance at a given time. Now, some things that we might need to come up with this differential equation in a word problem, we might need to calculate the Rn if it's not given. So we would need the flow rate of the liquid entering times the concentration of the substance. So maybe it's like a salt water substance. So the concentration of salt in the water would be that concentration of substance in liquid that's entering the container. And R out would be the same. So the flow rate of the liquid exiting times the concentration of that liquid. Now, sometimes we're not given the concentration. So if you need to be able to calculate the concentration, well, that's the amount of the substance divided by the volume of the container. Okay, so let's look at an example where we use these formulas to come up with a formula for x of t, the amount of substance at a given time in the container. Okay, so our example says water flows into a pond at a rate of 10 meters cubed per minute and out at the same rate. The volume of the pond is 1,000 meters cubed. Initially, the pond contains 100 grams of pollutants. So there's some initial conditions hidden in there. The concentration of pollutants in the water flowing into the pond is 2 grams per cubic meter. Assuming immediate and uniform dispersion of the pollutants, find a formula for the number of grams of pollutants in the pond. So we're looking for that formula x of t. Okay, so we want to create that differential equation dx dt equals the rate in minus the rate out. So we need to calculate those rates. Okay, so the rate in is going to be the flow rate times the concentration, and the flow rate out times concentration for R out. And remember that concentration, if we need to calculate it, is the amount of the substance divided by the volume here of the water. Okay, so looking at our rate in, they tell us that the water's flowing in at a rate of 10 cubic meters per minute. So there's my rate in, and it's the same out, so I'm going to use the same value for both of these calculations. The concentration, it said, was 2 grams per meters cubed. So we have the rate in is going to be 10 times 2, or 20 grams per minute. Okay. For the rate out, well, that one's going to have a variable in it, which is not surprising for us. A lot of these, you'll end up with a variable somewhere. Here, again, the flow rate is 10, but the concentration is not given, so we have to calculate that. So they tell us the volume is 1,000, and we don't know the amount of substance, so the concentration for the liquid flowing out is going to be x over 1,000, so x over the volume. So simplifying that, I get x over 100 grams per minute as my flow rate out. So plugging that into our differential equation, dx dt equals the rate in minus the rate out, looks like this. Dx dt equals 20 minus x over 100. Okay, so to find the thing that they're asking us to find here, the x of t, we just need to solve this differential equation. So you might notice that this is a linear differential equation, and it is separable. So I'm going to use the method of separation of variables to solve this differential equation and get the x of t they asked for. Okay, so dx dt equals 20 minus x over 100. I can divide by everything on the right to get the x's all on the left side of the equation and multiplied by dt. So I end up with dx over 20 minus x over 100 equals dt. And using separation of variables, the next step is to take the integral of both sides of this equation. For the left side, this does require u substitution. It's worth it to write it out, even if you feel pretty comfortable with doing some u substitution in your head. Here, the u would just be the entire denominator of 20 minus x over 100, which means that du is equal to negative 1 over 100 dx. Substituting that into the left side of our equation, I'm going to end up with a negative 100 out front times the integral of du over u. And now I'm ready to integrate both sides of this. So left side, 1 over u, that's just going to be the natural log of u. putting the u back, the value for u back in, I get negative 100 times the natural log of the absolute value of 20 minus x over 100. On the right side, integral of dt is just t plus constant of integration. I'm going to call it C1. It's going to change as I start to solve this for x. So I'm going to be renaming that every time the constant of integration changes. So first thing I'll do to solve for x here is let's get rid of the negative 100 that's out front. So I'll divide both sides of the equation by negative 100. My constant of integration changed because I divided it by a value. And now I have the natural log of that 20 minus x over 100 equals negative t over 100 plus c2. So next is to get rid of the natural log, and I'm going to get rid of the absolute value at the same time. I'm going to raise both sides of this equation to e. And then I'll throw a plus or minus on the right side of the equation to deal with that absolute value. So 20 minus x over 100 equals plus or minus e to the quantity negative t over 100 plus c2. Okay, so before I continue to solve and get rid of the 20 and the 100 on the left side, I'm going to clean up the right side. That c2 I can pull out, and it would be e to the c2 times the e to the negative t over 100. And then I can also throw the plus or minus into that constant. I'm going to take all that, wrap it up, and just call it c3. So I have c3 times e to the negative t over 100. And just because this is a long problem, I'm going to save myself some time. I'm going to subtract the 20 over at the same time. So now I have negative x over 100 equals c3 times e to the negative t over 100 minus 20. And just one thing left to do to solve for x of t, multiply by negative 100 to get my equation x of t equals ce to the negative t over 100 plus 2000. And there I have it. I have a formula for the number of pollutants in the pond x of t.